Hello, Chemistry 30. Today we learn the basics of chemical equilibrium. We're in a new chapter now, so we're going to learn what chemical equilibrium is, how we get a chemical equilibrium, what conditions need to be met, and then we're going to learn a little bit about equilibrium positions and stuff. So this is a lot of kind of laying down the theory work before we continue on and learn how to actually do things, skill, mathy type stuff around this unit. So first of all, these are the objectives we're covering today. We're going to define equilibrium and state the criteria that applies to a chemical system in equilibrium. And we'll talk about all these things after, and then also identify, write, and interpret chemical equations for systems at equilibrium. So we're going to learn as well what kind of symbols and stuff we can use to represent the fact that we have a chemical equilibrium. So first of all, here's the thing about chemical reactions. Although you've been told that they are all quantitative, so all reactants turn into products in a chemical reaction, that is not always the case. In fact, very often it is not true that a chemical reaction completely goes to products 100%, but instead sometimes it only partially goes to products, and often it's actually even just a little bit of product is formed, and most of the chemicals actually stay as reactant. So it's not always a 100% kind of completion thing. Now, what's interesting about chemical equilibriums is even though it might not go completely to product, that doesn't mean that things aren't still happening, right? So let's say that a reaction goes 70% to products. So 70% of reactants turn into products. It doesn't just stop there. The percentage won't change. It will stay at 70%. But I'm going to have products that is formed, and at the same time, I'm going to have products that's turning back into reactant. Okay, so what this means is I actually have a state that's called dynamic equilibrium. You learned about this back in Chem 20 when we talked about saturated solutions. So in a saturated solution, you learned that some solute will be dissolving, and then some of the dissolved solute will be crystallizing out of solution. But at saturated solutions, the rate of both of these things occurring is equal. The analogy is that if you go to a club and you have a lineup, right, with the bouncer there, that when two people leave the club, two more people from the lineup can go in. Now, the amount of people in the club is not changing, but the people that are actually in the club is changing. We have this all the time now with a little bit of COVID going around, right? So what we actually have is we have at stores lineups. So at Canadian Tire the other day, where as soon as one or two people leave, then another one or two people can go back in. The people in the store are always changing, right? But the number of people inside and outside the store is remaining the same. So when we think about the term dynamic equilibrium, it almost seems opposite, right? Dynamic, like an oxymoron. Dynamic means changing. If you talk about a dynamic character in English, it's a character that goes through changes as the story happens. And then equilibrium means like equal. So dynamic equilibrium means that the actual like chemical particles are changing. So I have change in terms of what particles are products and which particles are reactants, but my concentrations are staying equal. So another way of looking at this is that the rate of the forward and reverse reaction is staying the same. This is somewhat confusing to try to understand, but here's kind of the basic facts. At equilibrium, the forward reaction is occurring, the reverse reaction is occurring. So here I have an equilibrium written out to kind of refer to talk about this. So let's say I have sodium sulfate, calcium chloride that's reacting to make a calcium sulfate precipitate and sodium chloride. And let's say that I have an equilibrium for this reaction. So what that means is I have these two reactants that are meeting up in solution, right, and forming these two products. So that would be the forward reaction. But I also have this product reacting with this reactant, which causes the reverse reaction, so product going to reactants. When equilibrium is reached, whenever I have two reactants reacting to form these two products react to form these two reactants. So in other words, the forward reaction is happening at the exact same rate as the reverse reaction, and as a result, properties remain constant. you can actually track this. What they've done is they've done kind of experiments where they've taken things like radioactive compounds. So let's say, for example, that the calcium was radioactive. It was an isotope of calcium that has decay and lets out some radiation. So then they would kind of take a look and see, is it going into the solid in the precipitate, or are those radioactive particles within, the solution? And they could take a look at where those radioactive particles are. And what they could see is that it's constantly changing, right? That sometimes a radioactive particle might be in the solution, and then a moment later, it might actually be in the solid. Now, at the end of the day, the concentration, the amount of this stuff isn't changing, but the particles are changing all the time. The forward and reverse reactions are happening at the same rate. If I take a look at this comic, it's a great kind of representation of this, because what's happening is that I have snow moving from this sidewalk, right? From this one here to this one, and from the second sidewalk to the first one. So snow is moving in both directions, but the amount of snow on both sidewalks is staying the exact same. So stuff is changing, things are moving, right? Reactions are happening. But the concentration, the amounts is staying the same. And that's what the case is for equilibrium. Now, a bit of a misconception, people start thinking, oh, that means that it's half and half. Not necessarily. Okay, this could be a 98% reaction where 98% turns into this and only 2% stays as this. Okay, but the rate of reaction in that case would still be the same. Whenever I have a forward reaction occurring, a reverse reaction would occur as well. Okay, whenever one of these changes into this, then one of this changes into these. So the rate is the same, and as a result, once equilibrium is established and reached, the concentrations of stuff is staying the same as well. Now, I get an equilibrium when I have a closed system. So what that means is in a closed system, I have no matter exchange. So things cannot go into or leave the system. That doesn't necessarily mean that the system is actually physically closed. It could be an open beaker as long as I don't have any gases or anything that's being produced, right? So as long as I don't have anything going in or anything going out, then I can consider this to be a closed system. Now, you learned about open systems and isolated systems in the energy unit. When I have an open system, that means I have matter exchange and energy exchange, right? And then when I have an isolated system, that means I have no matter and no energy being exchanged. So looking at these two reactions, what kind of vessel would we need in order to get a closed system? So the first one, if I take a look at the states of reactants and products, I've got aqueous, solid, and aqueous. So for this, I could actually just have something like an open beaker, and that would be fine. That would still represent a closed system, because then I'm not having any product or reactant leave because nothing is gaseous, right? So that would be fine. Now, you might be thinking, well, what if something got in? Yeah, that would be an issue. So if we had some kind of chemical or gas that mattered coming into the reaction, it would mess it up. But essentially, we could just have this in an open beaker and that would be totally fine. Well, if we take a look at this system, it has a gas in it. So because I have a gas present, this would actually have to be full on closed, right? So I would need to have something that has a stopper on it or a cover that would prevent the gas from escaping, and that would be necessary for it to be a closed system. So essentially, all I mean when I say closed system is that there's no way for reactant or product to come in or to leave. That what I have is what I have, and that's it. All right, so different types of dynamic equilibrium we're going to be studying. The main one we're going to be looking at in Chem 30 is this chemical reaction equilibrium. But we do have phase equilibriums and solubility equilibriums as well. So when I'm talking about a phase equilibrium, a great example is water in the air, right? If I have water in a closed container, I do actually have some water that is evaporated and is in the air above the water in a closed container. So this comic is kind of around that. I've got these waters that are in the air in this closed system, right, that have evaporated. But then if one of them goes through condensation and ends up being, again, in this liquid water on the bottom, then a few more are going to end up leaving and they're going to evaporate. And that is a dynamic equilibrium. The particles of water that are in this air is always changing, right? But the amount, the humidity of that air is staying the same. Solubility is when I'm dissolving something, and that's one that you studied in Chemistry 20. So when I'm taking a look at a saturated solution, for example, I have all the time particles that are dissolving, and when a particle dissolves, another one comes out of solution and crystallizes. So the amount of dissolved solute is never changing, but the actual particles that are dissolved are changing all the time. So if I take a look, let's say I have some solid on the bottom and here's my solution, right? So I've got some solid here that is hanging out in a saturated solution. So saturated means no more solid would dissolve even if I added more. So max concentration has been reached. So when I have a solution like this, if I have one particle that ends up going into solution and it dissolves, then that means another particle that was in solution is going to now crystallize or come out of solution. So again, I have dynamic equilibrium. And the concentration is never changing of what is dissolved, right? But the particles that are actually dissolved are changing all the time. If I look at one particle, I'm choking on my own spit there. At one moment, it might be dissolved, and then in another moment, it might be the crystallized particle. And then in a chemical reaction, I'm of course dealing with reactants turning into products. So in this kind of system, I have all the time reactants turning into products, but then I also have products that are turning into reactants, and this is happening at an equal rate. So the forward and reverse reactions are both occurring equally as fast. All right, so summary of this. The following is true for a chemical system at equilibrium. It takes place in a closed system. It maintains constant properties. We didn't talk about that much, but when you look at a chemical equilibrium physically, the way that you can tell it's at equilibrium is because things are not changing when you're looking at the macro properties. So not looking at the actual particles themselves, but looking at the system. The color will stay the same, the pressure, the temperature, the consistency, it will all be staying the same, but that doesn't mean that the actual particles are staying the same. Things are still happening. And the big theoretical definition, this is the most important point, is that when I have equilibrium, I have equal rates of forward and reverse reactions. This is the equal in equilibrium. Okay, the forward and reverse reactions are the same rate. So if I have a homogeneous or a homogeneous equilibrium, what that means is that everything is the same state. So everything is the same state. So if I have an equilibrium where everything is a gas, for example, or everything is aqueous, or everything is, liquid, this is a homogeneous equilibrium. Okay. So let's take a look at a few equilibriums. This is in your workbook, so you can kind of take a look at that information and data and see what's going on. And we're just kind of going to do a little bit of a study of it. Doesn't matter what I start with for an initial concentration. If I'm looking at the same reaction, in this case, it's hydrogen and iodine, both as gases, making hydrogen iodide. It doesn't matter if I start with all reactants, like I have in system 1, or in all products, as I have in system 3. I reach essentially the same equilibrium position in either case. And this is kind of a neat mix of almost, a little bit of this and a little bit of that. If I analyze for all of these systems their equilibrium concentrations, the percent yield of these systems, I end up with the exact same number, almost, right? So if I take a look and calculate percent yield for all of these, I have 78% yield. 78, 77.8, 78.1. So essentially the same, right? Within kind of a small error range, I'm reaching the same percent yield. So I get the same equilibrium no matter what the starting point is. I could start with all reactants, I could start with all products, or like in system 2, a little bit of this and a little bit of that, and it still reaches the exact same equilibrium. So we can use percent yield to analyze this a bit, and we're going to deal with some percent yield calculations, but that's not actually the main way that we analyze these systems in math. We're going to learn in a future day something called equilibrium expressions, which is how we look at the math of this. So if I were to graph this, and this is a case where I start with all reactants and no products, right? I have high H2 and I2, and then I have zero HI to start out. This is the graph of concentration, or quantity as they put it, over time. So the question is here, well, I guess number one, we'll go through it in order. How does the amount of product change as the amount of reactant changes? I feel like this is really common sense, but I found over the years teaching classes that it isn't. In order to make products, I have to use up reactants. So if products are going up, that means the reactants are going down, and vice versa. If I have increasing reactants, I must be using products to make them, right? So when I'm talking about ingredients to make something, I have to use up ingredients to make the thing I'm making. If I'm making cookies, then I've used some flour and some sugar and some eggs. So I now will have less flour, sugar, and eggs than I had before. I can't unmake cookies though. And why would I want to, right? Cookies are delicious. But if I take a look here, as I have more products being made, I have less reactants. So how do we put this? More products as reactants go down. Indicate the time when the equilibrium was established. I don't actually have a number here, but what I'm looking for equilibrium is that I no longer have changes in concentration. So that would happen right about here. Yeah, this is the point where concentrations are staying equal. So now the next question is product still forming? Am I still making HI, right, hydrogen iodide? And that is a big yes. At equilibrium, I'm still making hydrogen iodide, but I'm also making at the exact same rate hydrogen and iodine. So again, the forward reaction and the reverse reaction are happening at equal rates so that the concentration is staying the same. So explain, yes, but H2 and I2 are being formed at an equal rate, would be the answer for that one. Okay, moving forward. So percent yield, how I calculate that, and you've done this in Chem 20, so this shouldn't be new to you. But to calculate percent yield, I take the actual yield, the experimental yield, so that's how much was made in the lab in the experiment, and I divide that by how much should have been made, how much would have been theoretically possible. Okay, so if I take a look at stoichiometry, this will tell me my theoretical yields. Well, my actual yield typically comes from the question, and this is what actually got made in the experiment, right? So actual is the same as experimental. You're going to see both of those terms. Theoretical will almost always be greater than the actual yield. It could be equal, but I'm never going to have more actual yields, like more yields than I should have gotten theoretically. If that happens, I have an impurity mixed in, but I can't make more product than I had reactant. And it's really important that I'm dealing with the unit and chemical being the same as well. I have to be comparing apples to apples, not apples to oranges. So if I have my actual yield in grams, my theoretical yield would have to be in grams as well. Or I could do this work in moles. I could have actual yield in moles and theoretical yield in moles. And again, it has to be the same chemical that I'm dealing with. So let's take a look at a question and see if you can work it out. So what is a percent yield of hydrogen chloride gas from hydrogen and chlorine if 1 mole of chlorine is reacted with 2.5 moles of hydrogen and only 0.25 moles of hydrogen chloride gas is produced? So this involves, first of all, some stoichiometry and dealing with how much hydrogen chloride should I have been able to make. So I'm going to go ahead and first write out my reaction as an equilibrium. So I have hydrogen gas, and I have chlorine gas, Cl2 gas. And this gives me 2HCl gas. So I have 1 mole of chlorine, and I have 0.25 moles of, oh, no, wrong thing, 2.5 moles of hydrogen. So this is actually a really simple limiting excess question because it's all 1-to-1 for H2 and Cl2. But if I take a look at this, Cl2 is obviously limiting because I have only 1 mole of this compared to the 2.5 moles of hydrogen. So based on the information I have, I should be able to make, theoretically, 2 moles of HCl because it's a 2-to-1 ratio. So my theoretical yield for HCl, if I'm dealing with moles, which is what I have for a unit, should be 2.0 moles. Now, I had 0.25 moles of hydrogen chloride actually made. So actual is equal to 0.25 moles. So my percent yield is equal to actual divided by theoretical times 100%. So I have 0.25 moles divided by 2.0 moles times 100%. And that's going to give me 12.5%, right? So I got a 12.5% yield from this. So that's my equilibrium position, is 12.5% yield. So now going back to what we talked about before, am I still making HCl in this reaction when it's at equilibrium? Yeah, HCl is still forming. I still have H2 and Cl2 reacting to make 2 HCl molecules. But whenever that happens, then an HCl molecule, well, 2 of them will react and form H2 and Cl2. So the forward and the reverse reactions are happening at equal rates. So this means that I have equilibrium, and one way that I can represent equilibrium, that I can show that, is first of all, I'm going to start using equilibrium arrows. And how I draw equilibrium arrows is it's just kind of like these 2 halves of an arrow. So I have this forward arrow, right? And then I have a reverse arrow. And they're equal size, and the idea here is showing that I have the forward reaction happening and I have the reverse reaction happening, and that they're equal in rate, hence the equal size. Percent yield, if I know it, if I know the number, then I would actually go ahead and just put the percentage over top of it. So if I went back to my previous example, now that I know this, first of all, I should change this to the equilibrium arrows that we now know how to do. And then I have 12.5%. So I know what the percentage is for this reaction. So the other example, if I have H2 and I2 to make 2HI gas, and that's a 78% yield, well, I know that this is an equilibrium. It's not a quantitative reaction. It doesn't go all the way to products. And I know what the percentage is, which is 78% yield, and I have that over top of the arrow. If I don't have a very exact equilibrium percent yield value, I can just use these really general ones to represent it. So first of all, if I have non-spontaneous, so nothing really happens, well, I don't put an arrow, and maybe not even products at all, just meaning, hey, it doesn't happen. If I have something that's reactant favored, so that means I end up with more reactant staying and not changing into product, then I have product forming, then it's a less than 50% reaction. So the yield is lower than 50%. So if I was talking in general terms, that example we did, that was 12.5%, that's a reactant favored equilibrium. If I have greater than 50%, that's product favored. So I would show the words just product favored, and again, these are general terms to refer to an equilibrium, as a greater than 50% symbol, again with my equilibrium arrows. And then finally, if I know that it's quantitative, in other words, almost all the reactant turns into product, say 100% reaction, well, then I use my classic chemical reaction arrow that I've always used in the past. And that actually has this new meaning now, that it means that everything goes to products. It is 100% reaction. Okay, so every little bit of products that could form for reactants is going to. So generally, that's how I would write this out. I've got a few examples here, kind of trying to sample using these arrows to show you the correct use of it. And then after that, we're actually finished. So I'll do the first one with you, and then I think it's probably good for you to try out, 2, 3, and 4, and then take a look and see if you've got it. You don't even have to try out the full reactions if you want to. Just try to figure out what would the arrow look like. So for example 1, hydrogen gas reacts with oxygen completely to form liquid water. So I have, of course, hydrogen gas is H2 gas, reacts with oxygen, so that's O2 gas, and that forms liquid water. Now it's a complete reaction, so using these general terms, that means it's quantitative. So I'm not showing an equilibrium arrow at all. I'm showing my classic chemical reaction arrow, which means all of it is turning into the product. I need to balance this, so I need to put a 2 on here and a 2 on here, and I'm finished. All right, for the rest of them. Oxygen reacts with fluorine gas to form oxygen difluoride. The reaction is product favored. Notice it doesn't say like it's quantitative or complete, but just that products are favored in this. So I have O2 gas plus F2 gas, and that's going to form oxygen difluoride, so that's OF2 gas. Now, if this is product favored, then I'm going to have my equilibrium arrows, and then I have a greater than 50% reaction. Okay, so that's how I would draw that one out. I need to balance this, so I'm going to need to put a 2 on my OF2 and a 2 on my F2 to make that work. For number 3, nitrogen gas, N2 gas, reacts with hydrogen gas, H2 gas, to form ammonia. This is a pretty famous equilibrium. This is called the Haber process. We're going to talk about this in depth when we talk about manipulating equilibriums in Le Chatelier, but yeah, so I have N2 gas plus H2 gas, and this says it's reactant favored. So now I'm going to have the less than 50% sign over top of that to show that most of it stays as this instead of forming the product of the ammonia. And again, balancing it with a 2 here and a 3 here. Finally, nitrogen gas is mixed with oxygen gas. Very little nitrogen product or nitrogen dioxide is formed. So I have N2 gas mixed with O2 gas. Very little dioxide is formed, so I have NO2 gas. What I would like to do with this, I think the best choice is still to actually show a little bit of an arrow, right? And then I could do something like less than 1% here if I want to be really general. Or if it's very, very little, I could even put approximately 0%. You've seen something like this in Chem 20 when we dealt with acids and bases to show that. So I even want to back up here and just do something where I kind of show it as this, and then say, let's say, approximately 0% or something like that. But I think it's important to still show some kind of arrow, okay, to represent that, hey, it didn't happen, right? Almost none of it actually occurred. Here I have very little, so I did have a bit, so I can put approximately 0%, just to kind of clarify what is happening. All right, well, that's it for today. I know a lot of loose ends there. We're all over the place. The big thing for a skill from this is reviewing the idea of percent yield and just being familiar with these different types of arrows that I can use for general terms representing equilibriums. And then the other big thing is the theory part of what the equal is in equilibrium, which is the forward and reverse reaction rate. And just kind of understanding the macro properties are staying the same. So things like color, temperature, pressure, those are staying identical when I have equilibrium. But the fact is that the particles that are products and reactants are constantly changing. Okay, so that's the dynamic portion, is that I still have reactions occurring. I have the forward and the reverse reaction occurring, but they're at equal rates. So at the end of the day, my concentration is not changing at all. It is staying constant for all reactants and products involved. All right, that's it. Enjoy the rest of your day.